Okay, and initiate screen sharing also. Although right now we are not really looking at OneNote. All right, now you can go ahead and ask.
Uh, Sir, the omega term, like in lecture 7, equation of states, page 9, you have
Mm-hmm.
told something about that, like when you had defined that for a pressure of -1, the temperature being some, like 1 by TR was where 1 by TR equal to 1 by point 0.7 something, and you told about omega, that the down we go omega is negative positive. Like that part was a bit sketchy for me. Like, how are you saying, how is, like you have drawn a two-head arrow and you had told omega varies, and you had told something like that was a bit not clear. What were you referring when you were saying omega is uh, like how are you varying omega there? So you had drawn three lines, three slopes, negative slopes, and over there one was for omega greater than zero, one was lesser, and one was omega at one. Uh,
Tell me,
ec-
so let
Lecture
me go to that
7,
figure
page
again.
9.
It
Lecture 7, page 9,
is
EOS, equation of state.
it would be in week 4, page 9, you are saying, right? Okay, perfect. Yes.
हम्म So ये जो आपने W वाला डबल हेड एरो बनाया W के पास में like in the graph, uh,
Mm-hmm.
what is that representing? Like, what is it? Like I was not able to. What did you info when you made the double head arrow near W,
Mhm.
like
So,
that
so,
line?
so number one, I am not making the arrow near W per se. Okay, I mean, I'm marking it as W. So, the first thing to realize here is that this is this figure 3.13 we are using to define our three parameter equation of state. The three parameters are PC, TC, and omega, where
Hmm.
omega we call is the parameter that quantifies interactions and geometry both. Okay, so you might have species with different geometry, you might have species with different interaction strength. For example, ammonia will make hydrogen bonds, CO2
Hmm.
has codopolar nature.
Hmm.
Okay, whereas your noble gases, argon, xenon, neon, they only have the so-called van der Waals or dispersion interactions, no additional interactions. Okay, so that is what I mean by the nature of interactions. So now in this three parameter equation of state, we wanted to define the third parameter. And that third parameter is based on the observations in figure 3.13. So let's say the data in figure 3.13 is experimental data, where on the y-axis we are plotting the logarithm of saturation pressure in reduced units. So we're dividing by PC. On the x-axis, I am plotting the inverse temperature again in reduced units. So dividing by TC. Okay. And when this data was plotted, what it was observed was that even though the values are different for different species, for example, the black line refers to argon, xenon, neon. The red line above this black line refers to hydrogen, helium, and the red line below this black line, for example, is referring to n-octane and maybe some other species also. Okay, so what was observed was that when this data was plotted for various different species, the data fell on a straight line. So these three lines here, two red and one black. The black one is the baseline, which we are using to define omega. And the two on the red are some other species. The one above and one below, I have marked the species also. Okay, for reference here. So what was observed was that even though these three lines, like you're seeing, these are different lines. So even though they were not falling on top of each other, however, all of them were roughly falling on a straight line. And therefore, we said just a single parameter can capture this deviation. That single parameter can be slope. So I've also marked the values of S on the three lines. So either I could have used the slope or one more even easier parameter, which was defined, or rather than calling it easier, let's call it alternate. So an alternate parameter which was defined was omega here. And now we are quantifying omega using this figure 3.13. So on this curve, directly on either axis, omega is not present. On what is actually present is logarithm of PR sat versus 1 by TR. Okay. And then we just picked one specific point where the black line value on the y-axis was -1. So again, just for convenience purposes, we picked that point. And then we came to equation 3.20, that is defining omega on the basis of data in figure 3.13. And the reason we were able to do that was figure 3.13 for each species is characterized by a single parameter, which is the slope.
So just to sum up, we were able to uh, relate this graph and relate its attributes to a single parameter was because we were able to see that it was only like that was the only thing which was making it vary. Like that
Yes.
was another.
Yeah.
Hmm.
So actually, to turn it around, let's say first the data came.
Okay.
So first, this observation came that the logarithm of saturation pressure in reduced units plotted as a function of inverse temperature falls on a straight line for a variety of different speeds. So first this observation came. On the basis of this observation, then someone said, okay, that sounds nice. That means I can now use three parameters rather than two to define the equation of state for a variety of different species.
This is like the eccentricity, right?
Yes, yes. The third parameter is eccentricity. Okay,
Hmm.
and so just to kind of in short to say, uh, if I ask which came first, figure 3.13 or the three parameter equation of state, the answer is figure 3.13 came first.
But we had already had an idea that the results which Wonderwall gave were not right, right? Like he was missing a factor. And so didn't they get any hint that they need another parameter? Like that's how you also
No,
introduced
no,
omega,
yes,
right?
there was there. Yeah, no, so that was clear. That's why the attempt was made to go beyond
Hmm.
the two
Hmm.
parameter equation of state. But whether it would be three, four, or thousand parameters, that idea was not available.
Okay.
Okay,
Hmm.
and even three is not sacrosanct. If
Okay.
I want water, three parameter equation of state fails.
So I
Okay,
can
if I
get you.
want supercritical CO2, three parameter equation of state fails. I need more. If I want
Okay.
hydrocarbons at conditions being used in the oil and natural gas industry, three parameter equation of state fails. Okay,
All
so
right.
in that
Hmm.
sense, it is not sacrosanct, but for a very large variety of species and a very large pressure and temperature range, it is quite accurate.
Okay. So the thing which you're also trying to say is the slope is not omega, and that's why you defined it separately as omega, and just try to show that that is the thing which can vary, and we can see based on that, right?
Yes, and
And
the slope values I have mentioned. If you look up the two red
mhm.
lines, I have referred to the slope value also.
Hmm.
Okay,
Yeah,
and then we are using that to find omega.
using the slope to find omega. Okay, so from the
You can
equation
say
given
either
below. Hmm.
slope or the value at that point. So if it's a straight line, slope will tell you the value, value will tell you the slope.
Hmm. So basic, but we need a reference point, right? To
Reference
come.
point is all of them you can see are going to zero.
Fair enough. Yes. Sir. Hmm.
Okay.
Hmm. So, like in the beginning of this part, you had told that there are five parameters: A, B, temperature, pressure, and V, specific volume. And that's how we start, and then we find relation between A and B, and then we find to put it better in critical parameter terms like TC, PC. We introduced PR, which is relative. So, why do we need like if we know temperature and pressure, like two fail, won't most of the cases be covered? Like generally we only need at max two parameters, right, to vary. So like
No,
gen
not clear. Say it again.
so like whatever I understood, even in the PV diagrams when we using Gibbs phase rule, two parameters, temperature and pressure. Like if you have those, then you can then all others become redundant in some way. Like if you have a function of temperature and pressure, then if we have another function of temperature, pressure, and volume, then that would have it can be represented as a function of temperature and pressure in combination of something like basically what I understood was temperature and pressure were is sufficient to define a gas.
Yes.
uh,
So yeah. So that is absolutely correct. That if I have pure species, then just two parameter values, two intensive variables gives intensive variables. Let's say pressure and temperature would be sufficient to fix the intensive state. Okay. Beyond. Okay. After that.
But when like I think it's in this lecture, I'm not very sure, but then you had told there are five parameters which you require: temperature, pressure, volume, A and B.
No,
Uh,
I'm not. So it's in this lecture only. So I'm not saying there are five parameters. Okay. So what you have to realize is, so actually you go to the very beginning of this lecture where this concept was introduced.
yes, sir.
That the Gibbs phase very rule says that there must be a relationship between P, V, and T. Okay.
Their inflection point, I think.
No, no,
There.
nothing about inflection point. Just yeah. So this one is the starting point. Okay, that what this is the starting point of what you were referring to. That if I know P and
Yes, sir.
T, all other intensive variables become fixed. Okay,
Hmm.
so that was done. Let's say before. In a way, that is the starting point for us. That okay, if I know these two variables, everything else will have a fixed value. So the entire chapter is now focused on what are the different. So I don't know what is f, but the functional form of f is not available to me. All I know is such functions, maybe one, maybe more, depending on the accuracy. If I am 100% accurate, it will be only one, but I'm never 100% accurate with equations of state. Therefore I have multiple options or multiple equations of state. Okay, so what I know from Gibbs phase rule is some relationship must exist. Now all of the work which is being done in this chapter is to find out those relationships. So that means I need to know what is the functional form of f, because only then it will be useful. Okay, it's one thing to say that if p and t, if you know p and t, you would know v, but it's a very different question to then ask you what is that value of v. So you know that v will have a unique value, but without measurement, can you tell me what is the value of v? That is what equation of state is telling me.
Okay, sir.
Okay, and now to the question of five parameters. So those a, so if I look here, right, equation 3.14.
Hmm.
So you can see here there are five variables: P, R, T, V, A, and B,
Hmm. For
where A
cubic.
and B are species specific parameters. So all of the next set of works was to find out A and B. Okay, so
Hmm.
if I know A and B for a given species, then you can clearly see from equation 3.14. If I tell you P and T, you can tell me V. If I tell you V and T, you can tell me P. If I tell you P and V, you can tell me T.
If we know A and B.
Yes, I mean A and B are
Yeah.
species specific parameters, right?
Species specific. Yeah. Hmm.
And that argument now translates to other equations of state also. If there are more parameters, like three parameter equation of state, then you need to know three things about the species. Okay, now next work was just to express A and B in terms of other widely available measurable properties, which were PC, TC, VC.
Okay, so fine.
Okay, so
Hmm.
A and B are unknowns, PC, TC are also unknowns. A and B are species specific, PC, TC are also species specific.
Hmm.
Okay, so
So
all we did was converting A and B into PC, TC.
okay, so that we have a better like because those are more widely known
Yes, exactly.
parameters.
Yep.
Uh, so, but now a question regarding the crit. I don't know if others would have be having doubts. Like I'm just
That's okay.
sorry, but
You can continue. We will have enough time because Thursday is also available. Yeah, tell me.
okay. So, like the now this would be a bit shift from this to the initial lectures because I had this doubt since the beginning, but like it was not a very concrete doubt. So, at critical point when we had the PET curve, uh, at that point, so you had told about supercritical fluids and stuff like that. So over there, the you had so is the like the critical point just if I have critical point as point C, if I just go above isothermally. Uh, would that point be called a superfluid, or like you have to go to the right side as well? So, is there any very specific condition for me to reach from point critical point to some supercooled fluid or some?
So supercritical fluid requirement is P must be above PC, T must be above TC.
So that is like going in a like
So
both
even if you
left and
go,
up.
I
Yeah.
mean, depends on which graph you're talking about. If you're talking about
Hmm.
PV, then I don't know. Are you talking about
Yeah.
PT or PV?
PT. PT.
On PT, yes, you have to be above PC, above TC.
But like in the curve the graph which you drawn for that, it was not very like I would expect you to have a quadrant basically from point like imagine that the origin translate the origin to the point the critical point, and now that quadrant on the top and right that would belong to the state which is supercritical. So, but
That's
how it
exactly what we have, right? So on figure 3.2, if P is above PC, T is above TC, that is the quadrant which I am quantifying as a supercritical fluid. Now this dash line you can say belongs to both. Okay, this dash line you can put in L, you this you can put in, so P equal to PC, T greater than TC is also supercritical fluid.
okay, okay.
Okay,
You mean
but
the
we
dashed
have
line,
a
right?
quadrant. Okay,
I thought that, yeah, I thought that this was not a quadrant, like it was a curve. That's what I remember. And why I
no, so
had,
that's so I have dashed lines, right? I have vertical dashed lines going from C and horizontal dash line going from C. So whatever is in that part, right?
hmm.
That is your supercritical fluid.
So the quality of supercritical is now you can't compress it to a liquid. The difference between a liquid and a vapor is lost. That is one, and
Mm-hmm.
but the other is you can't even compress it, right? You had told something regarding this is
Isothermally, you cannot
I
isothermally compress it to a liquid state.
okay. And regarding transportation, you had told its viability, like the mass increases. Like,
Mm-hmm. Mm-hmm. So the nice thing about supercritical fluids, so if let's say, um, if you want to look at applications, right, it has both liquid like and vapor like properties. So let us take example of supercritical CO2. Okay, so supercritical CO2 is a sometimes known as a green solvent.
okay.
It might sound counterintuitive that we have CO2 and we have green in the same sentence. Okay, but it is correct. So why supercritical CO2 is green solvent? Okay, so supercritical means I have both liquid and gas like properties. So for a good solvent, the liquid part is it must be able to solubilize. Okay, so supercritical CO2 can do that. It has high density, small polarity, apolar characteristics also. You have a carbon there. Okay, so it has a quadrupole, but it's not very highly polar, so it can be used for apolar solvents also. Now the gas like qualities which help for supercritical CO2, diffusion. Okay, so what that means is if I have some material, okay, maybe it's a porous material and there is some liquid inside this pore, I take supercritical CO2. So this is a porous substrate, and now the supercritical CO2 would be able to enter this porous substrate much more easily compared to a liquid. So the gas-like properties of supercritical CO2 are also coming to my benefit. Okay, it has high diffusivity compared to a liquid, high penetrability inside small pores, which is beneficial to me. Okay, so because of these reasons, supercritical CO2,
Would you call it the fourth state of matter?
mm, or I cannot, but others are also not. So yeah, therefore I'm not calling it as a fourth state. Okay,
No, but if it's not like it is,
it
and
is a
other
fluid. I mean, depending on what conditions you are at, it might show very liquid-like behavior or very gas-like behavior. Okay, so even though we're saying it has both liquid and gas-like properties, it will depend on its P and T values also. So depending on pressure and temperature values of a supercritical fluid, it can be very much close to a liquid, very much close to a gas, or in between. Okay, and that's where the application comes. Okay, so this supercritical CO2, it's not that you can use at any P and T supercritical
Okay.
CO2, it will
Hmm.
behave like a green solvent. So you have to
Hmm.
optimize it according to your application. Okay. So you have
Fair
to
enough.
go to conditions where the viscosity is matching to your target value. So the nice thing about supercritical solvent fluids is that properties can change a lot with change in P and T. Okay. Both liquid like as well as gas like properties can change a lot with P and T, but you will need to adjust P and T. Okay. So it is able to replace some organic solvents because it has apolar character. So it is able to
Okay.
replace some hazardous organic solvents. Therefore, we call it as a green solvent. Okay.
But as you took the good qualities, you would have taken the bad qualities of both liquid and gas, which are not favorable, right? I mean,
So that's why I said that you have to adjust P and T so that
hmm,
you are able to
optimize
optimize
it.
viscosity, diffusivity, solubilization, which is density and depending on polarity at those conditions. So you will need to optimize all those. Okay. You might do a large set of experiments to design the conditions, or you might use some theory, equation of state of CO2 to help with design of experiments. But you will need to do optimization to understand at what conditions you have to use supercritical CO2.
Okay, sir. One more doubt was you had no. This is so. I mean, the doubts a bit scattered. I
Okay,
just
so
jotted
let's
them.
hold on and let me give floor to others, and then I can come. Okay, there are not
Sure, sir.
all people. All right. So anyone else? Any questions, queries, any problem solving doubts? So probably Sarthak has driven others away. Anyways, yeah, Sarthak, go ahead. You can ask what you were asking.
Yeah, that was my fear while beginning the thing. Okay, so basically what happened was last week I had COVID, so because of that I lost the momentum, and then this. So just yesterday I just covered a magnificent bit of it. So I just had doubts uh, which I had. V equal to ZRT by rho is what by P is what you had given, but there's from the part where my doubt came about specific volume. So you told that now over here in that this is I think in the last lecture which you the eighth lecture which I saw. So eighth or the seventh lecture where you had told about in the end you had concluded that we get V and V equal to ZRT by P is what you use. But over here then this V should be V by N and not V by mass. But you told it's V, so how are you
No,
justifying
so
that?
we will depend on other. So we can be specific volume, or it could be molar volume. So we are using the same volume, same symbol, but it will depend on the context. So like as you pointed out, if it's
Okay,
R hanging in there, it's a molar volume.
fair enough.
So we are using the symbol interchangeably, and that is true for all other quantities also. H, S, all other quantities we are using interchangeably. Specific versus molar, we are not defining separate volumes or separate symbols.
Fair enough. So the context is key there.
Yes.
Yes, right. And if I were to, like, I think for now doubts are clear. And one thing, my favorite line was, favorite line till now from all the chapters was when you told as we get to high temperatures, we unlock more degrees of freedom. Like that point just was very like chamak gaya types feeling came when you had told that it unlocks more degrees of freedom. It was a very nice
Mm-hmm.
part.
Good. Good.
Yeah. I just mentioned because it was really cool. Like when I heard it, when you say unlock, it just gave a new dimension to the talk. I felt.
Okay. Great. All right. Any other questions?
So when you
Thirdly, I would
say
highly recommend others who might listen later that solve problems. Okay, it's critical. Yeah, you were saying something.
so regarding meta stability, I had seen another doubt session which you were having, and in that there was a question, and you had even given a video you for a particular like when we give disturbance. So what kind of disturbance are we considering as disturbances? Because they would have some thermodynamic backing, but disturbance, right? Like would a
Yes.
electrical jolt be also called a disturbance?
Depends. So I mentioned that it's a nucleated process. That means it is
Mm-hmm.
the change in state is separated by a barrier. It requires an energy input. So whatever perturbation gives that energy input to allow that change of phase from one state to other is the thermodynamic jolt or thermodynamic perturbation required to cause the effect.
And then it is instantaneous. Like then because it is having a easy like lower energy state, so it will just travel to that.
Depends. So that is in some sense beyond this discussion. At least what we discuss here, but in a different course, I talk about kinetics, phase change kinetics. There are two ways by which phase change can happen. One is known as nucleated, other is known as spinodal decomposition. So that will determine whether it is instantaneous or and what you call as instantaneous. If it happens in 1 millisecond, is it instantaneous, or do you require it to happen in 1 microsecond or 1 nanosecond? Okay, so all of that comes to kinetics, which phase change kinetics, which in this course we do not discuss at all.
So could you open that part of the lecture? I had a doubt where uh, in during that part where you had told that there was a graph there, and you had told that the right hand side is the solution and the left hand side would be the metastable state. That's what I
Tell
remember.
me which
This
page.
would be hard. I didn't note this down, but I had this out. I had sent it to one of my friends, and he also did not get it.
You
Uh,
can go to phase diagram.
Metastability. Yeah, it is metastability.
This probably we have come too far ahead.
So it would be below. Yeah, somewhere here. Mm.
I can draw it again, but I just want to, if
So the
possible.
roots, basically, how can you say which, like when you get the roots, how can you say which root would be,
Yeah.
say,
Yeah. So here I believe somewhere it is there. Yes. So figure
mm-hmm,
three
this
point
part.
ten. So now you can ask.
So over here, that's now what I understood was you had so over here there was PSAT, which was one reference which you had taken, and then below that you were saying it is intersecting the isothermal curve at three different places. And you had told that the second one was not accepted because of the slope, because it was having a positive this thing. So you had the other two, and now over here, automatic like for me there was a gap because you had told that the state three would be a state which is stable, and state one would be like the E state would be the metastable state. Uh,
Mm-hmm.
but how did you decipher that which one would be metastable and uh, which one would
Because
be
the black curve is showing you equilibrium expectation. So the black curve is saying that if you are on the right, that means to the right of CD, you are in a
Mhm.
vapor state. If you are in between, you are at coexistence. If you are on the left, you will be in the
liquid?
liquid state. Okay.
Mm.
So if I forget the red line, okay, and just look at the horizontal line PE, and on that horizontal line PE, 3 points E, 2 and 3. Okay. So I can clearly see that point 3 corresponds to the equilibrium answer, which is basically saying that I'm at a pressure and temperature, or you can say I'm at a specific volume and temperature, whatever you want to choose. It doesn't matter. Okay, but I am point 3 is the vapor state. The point 3 pressure is PE, and point 3 volume is, you can say, whatever corresponds to V3. So let's try to draw this again with some deletions. So I will keep the equilibrium part, and let us say this is your point 3. Now I draw the isotherm which is passing through point 3. So I'm doing it in reverse. Okay. So I know at 3 P and V, it is a single phase. So I'll be able to know what is the temperature at this point. Okay. So we are calling that temperature as T2, which I am obtaining. Let's make it T3. So forget about figure 3.13. So if I knew P3 and V3, I will be able to calculate T3, okay, from some equation of state. So I've done that. And once I do that now, I'm going to draw an isotherm at T3. And that is how that will look like. That is the actual isotherm at T3. And from here, you can clearly see that point 3 is the equilibrium answer. Okay. Whereas it is possible that you go up to some state E where even though your phase diagram is predicting that at this particular point you must have been at coexistence, however you are not at coexistence, so that means you are not at equilibrium. Okay, and the specific observation was the mythbusters experiment, where you take liquid water to a temperature above 100 degrees celsius at 1 bar, but you are still not getting vapor. Okay, so point E is your superheated water from the Mythbusters video. Okay,
So,
so the reason
so
I'm able to know E is not equilibrium answer is because my phase diagram is saying that E must have been two phase, but I'm not seeing two phases at E. I'm only seeing one phase, which is liquid.
because
Therefore, I
this,
know E cannot be the equilibrium answer.
so you're seeing two, okay, and so the condition favors only one state and you're seeing two phases. Uh,
No,
two,
vice versa. I mean, it depends on. So if I look at this point, so it depends on how you define that condition. If you define the
okay,
condition using P and V, then it favors 2 points, two
okay.
phases. If you
Hmm.
define that condition using P and T, then that defines a single phase, which is a vapor phase. So that just depends on how you are defining, because now E is no longer equilibrium, and because E is no longer equilibrium state, two variables are not sufficient to fully quantify state E. So I could have
Okay.
chosen P and V, or I could have chosen P and T. Depending on what you do, the equilibrium answer changes.
So according to Gibbs phase rule, the this thing would increase, right? The degree of freedom would, like, we would need more intensive variables in the in the coexistence region to
No, no, no.
define.
So you need, but E is not equilibrium. Gibbs phase rule only applies to equilibrium phase.
Okay,
So
makes
Gibbs
sense. Yeah.
phase rule doesn't
Mm,
apply to E if E is the metastable state.
fair enough. Okay. So that means that E can be defined by with the, like, if you are taking temperature, then only PT, then only one parameter. Only.
Yes, if it was two phase. I mean, if it's at equilibrium, then yes.
Okay. Okay, fine. When you drew the curve in the notepad. So when you drew yours T3, that was parallel to the x-axis, whereas over here it is having like a slope. So you had told about this also, right? That some are actual and some are what we get mathematically. So like over here we are getting three roots, whereas the one which you drew on the right hand side of the page just now for
Mm-hmm.
explaining, over there
Mm-hmm.
you made it parallel to the x-axis. So generally, is
Because
it
that is
this?
the equilibrium isotherm. So if you go through the lectures, the equation of state we have discussed is incorrect in the coexistence region.
Mm-hmm.
So the red curve, the solid red curve in 3.10 is equation of state prediction, and the green curve I have drawn on the right is the actual
Actual one. Hmm.
equilibrium answer. One more chance, others. Any questions? Any queries? I will stop recording because uh, I don't think others will have or might not be as relevant. So let us stop recording.